Hello, this is the Venus Mine project. In this video, I will show the device of our architecture, its differences and advantages in comparison with the traditional architecture which is used to create modern computing devices. As you already know, each chip inside contains a silicon crystal on which the electrical circuit of the computing device is implemented. The density of the transistors on the crystal depends on the technological standards on which this crystal is produced. As you can see from this graph, each time the transition to the next technological level takes more time, and if the transition from 14nm technology to 28nm occurred in just 1.5 years, the transition from 12 to 7nm took more than 4 years. However, some companies haven't been able to master the 7nm technological process, and Intel still runs into certain difficulties at this stage of its introduction into mass production. Such problems in the development of microelectronics are associated with physical limitations that modern materials and devices cannot overcome. Technologies have come close to the physical limit at which the creation of integrated circuits is possible. Now they are frozen at the Mach 7 nanometers. The thickness of the boundary layer with this technology is within 30 atoms. Therefore, further progress to 5 and 3 nanometers will take a good 10 years. All this time, the number of transistors that will be available to engineers for the development of computing devices will be limited, and this has already stopped the productivity growth of Bitcoin miners based on the rapid change of technology. In this situation, improved architectural solutions will be the only way to improve their performance. Our project is the first in the miner building industry to offer such a solution. Well, meet SHBA, Serial Hashing Bitcoin Architecture. Serial architecture is built on the principles of serial data processing that was invented at the dawn of microelectronics development along with the classical parallel architecture. However, in those days, the serial architecture was significantly inferior to the parallel one in performance. It required exact synchronization of data input and output. It didn't allow to build large combinational devices, and most importantly, it required a lot more clocks to process the input data than the parallel architecture, and therefore was considered very slow. As a result, the parallel architecture was chosen to build most of computing devices. At that time, it was the fastest, and they simply forgot the serial architecture over time, although they shouldn't have done it. The time was getting on, technological nerves decreased, clock speeds grew, and the bit count of the data bus increased from 8 bits to 64. Engineers learned how to build fast clock generators directly on a silicon crystal, and by insensible degrees the advantage of parallel architecture shifted to serial one, but no one has noticed it, therefore one had to invent it again. So, let's get acquainted with the differences of serial and parallel architectures. In this picture, you can see the main difference between parallel and serial architectures. In the parallel architecture, all the data for the calculations enter into the computing device simultaneously along parallel conductors. In exactly the same way, the result of calculations is simultaneously output from the computing device along parallel conductors. In the serial architecture, all data enter the computing device one after another, one by one, for each data block. In one cycle, only one bit of data is sent to the computing device for each conductor, and only one bit of the result of the calculation comes to the output. Let's take a closer look at the operation of these devices on the example of an 8-bit adder built on the principles of serial and parallel computing. To begin with, I propose to consider how the classical parallel architecture works. On the left you see two inputs for 8-bit numbers. On the right, one 8-bit output for the result of the addition. Let's choose any two-digit numbers to add. For example, 57 and 82. Their sum is equal to 139. Now we will convert these numbers into a binary number system using an engineering calculator. Next, enter these numbers into our adder. Having entered the first number, we already see that the result appeared on the output, which is equal to the first number. It is simply the result of adding with 0, which is still the second input. Now we enter the second number of summation and we get the result of calculations. Let's copy this binary number into calculator and convert it into a decimal number system. As we see, the result of the addition is correct. We received 139. All addition operations in this case occurred instantly. This is in one clock cycle. This is how parallel architecture works. Now let's see how the serial architecture works. So that the input of numbers could be performed bit by bit, at the inputs and the output from the adder, we have to collect small shift registers from D triggers. Let's enter the given numbers to the inputs. We need the next action to enter our numbers in these registers, which will constantly shift them in the direction of the adder. Click Load. Now we can see that these numbers appeared inside the shift registers. Let's perform the first addition step. As you can see, the first one appeared in the first cells of the output shift register. This is the result of adding the last 2 bits of the incoming numbers. Let's continue the addition by completing other 7 clocks. During the whole process of addition, you can observe how the numbers shift to the right to the input of the adder for each clock cycle by 1 position. And at the output of the adder, the sum appears, which is just constantly shifted to the right the same way. Now when we have finished the addition, let's enter the result into the calculator and make sure that the result of the addition is correct. Therefore, we see that we received the necessary amount, 139. This means that our serial adder works correctly. After saying all this, someone may ask, and what is the benefit of the serial architecture if it requires much more clock cycles to calculate the result? Well, now when you understand the difference between these two architectures, let's look at the advantages and disadvantages of serial architecture. You already know that the only disadvantage of the serial architecture is that it requires as many war clock cycles as there are bits in those numbers that need to be processed. But it has advantages. Yes, indeed, the parallel architecture does all the calculations in one clock cycle. However, it requires many computational elements. The bigger numbers that need to be processed, the more logical elements are required to create a parallel computing device. At the same time, the serial architecture requires only a few logical elements to create any computing device. When we looked at the work of the 8-bit adder with parallel data processing, you might have noticed that we needed 34 logical elements to assemble it. The same adder built on the principles of serial architecture required only 15 logical elements. The serial adder was half the size, but it worked 8 times longer. Thus, the parallel architecture is 4 times more advantageous for 8-bit computing devices. However, nowadays 8-bit architectures are used only in all microcontrollers, and all modern processors run on architectures that use 64 bits of data. Let's recalculate what will change for the 64-bit adder. A modern 64-bit adder requires more than 314 logical elements or more, depending on the type of the adder. At the same time, the serial adder still consists of only 15 logical elements, which is 21 times less. However, for the addition of such numbers, the serial adder requires 64 clock cycles. As a result, we can conclude that the serial adder still loses to the parallel by 3 times. However, it does not. The fact is that to perform its function in a parallel adder, the signal must pass through the entire length of the summing conveyor. As you can see, even a 32-bit adder has a very long conveyor. The one of the 64-bit adder is twice as long. Signal transmission through such a long conveyor takes a long time, and its working clock frequency doesn't exceed 600 to 700 MHz. That is why modern processors rarely operate at clock frequencies above 3 GHz. Nevertheless, in order for the 64-bit adder to work at such a frequency, it is more complicated, dividing into blocks and adding many additional logic elements. Such adders are called accelerated transfer adders, and they require much more logic elements for their assembly. And what can our serial adder do? The serial adder has a very short conveyor, only 16 gates, so it can operate at a frequency exceeding 20 GHz. Now let's count it. The serial adder loses to the parallel by 3 times in terms of the size and number of clock cycles, but it wins 32 times in a clock frequency. Thus, the total advantage of the serial adder will be 10.5 times. Certainly, we should note that the advantage of the serial architecture over the parallel one in Bitcoin miners is not so obvious. This is because Bitcoin hashing uses 32-bit numbers and not 64-bit ones. But even in this case, the serial architecture is a winner. But there is more. The serial architecture has another advantage. It has a low routing factor. The routing factor is the ratio of the area that the logic elements occupy in the crystal to the area that the wires occupy in the crystal. You might already notice that the parallel architecture requires a lot of wires for transferring data to computing devices. This picture clearly shows that 32-bit architecture requires 32 wires for 2 inputs and another 32 wires for output that together will give 96 wires. At the same time, the serial architecture requires only 3 wires, and all these wires take place on the crystal. Thus, if you combine all the advantages of the serial architecture together, we get a very significant performance increase, which can be factually used to accelerate the work of miners. Now I offer to observe how our architecture looks for hashing Bitcoin in a behavioral simulator. On the left you see the kernel management system. The kernel conveyor itself goes to the right. In its lower part there are multiplexers which in turn enter into the conveyor all the bits of the input data. Above the conveyor there are buffers for storing intermediate calculation values and digital indicators that show these intermediate results of calculations. In the course of work, you can see how the results of calculations shift to the right with each clock cycle, fill-in data buffers. In 38 cycles, 1 full round of Bitcoin hashing is performed. Let's stop the clock generator at the end of the next cycle of calculations and compare the result with the control values. As you can see, the number A65 completely coincides with the control 2FAAAE43. The number E65 also coincides with 55CA55AO. If we start the clock generator again, this data will move to the next microcore of the conveyor, and in 38 cycles we will get the following result. This time it will be the numbers of the 66th round, A66 and E66. For those who are slightly familiar with the hash protocol of SHBA 256, it may be surprising that only 2 numbers are calculated in each round, the number A and the number E. And where are the other 6 numbers, B, C, D, F, G and H, you will ask. But everything is correct. For each round of hashing, only 2 numbers are calculated, and the remaining numbers shift by 1 position and replace each other. For example, the number B turns into C, and the number C turns into D. This is easy to see if you look at the hash algorithm SHBA 256. Each of these numbers shifts over 3 rounds, and only every 4th round is processed. All these rounds have to be stored in buffers for storing temporary data that you can see at the top of the conveyor. After several rounds of calculations, it is abundantly clear. Let's stop the clock generator again and look at the results of our calculations and what is stored in the data buffers. As you can see, for several rounds, the numbers A65 and E65 are transferred to the buffers and travel along the conveyor until they take part in the last calculation, after which they finally disappear. The same happens with other numbers. For example, with the numbers A66 and E66, as we see, they also coincide with the control numbers, which tells us that the conveyor is working correctly. After receiving these numbers, they also get into the data buffers and travel along the conveyor until they are converted. Let's try to figure out how the microkernel of our conveyor is arranged. First, the presence of double-D triggers sticks out. Their task is to memorize 1 bit of incoming data for exactly 1 clock cycle and then transfer this bit further to the next trigger or computing device. In this scheme, they perform the role of synchronization devices, which allow all data to be entered into computing devices with an accuracy of up to 1 bit. The following devices that you can see in our circuit are the serial adders. They are designated as POSUM. You have already seen their work before, so we will not stop on them. There are also 2 computing devices in each microkernel called MA and CH. As you can see, these are simple combinational devices that consist of only a few logical elements and take 3 different numbers as input and send out as output. Well, the most complex computing devices that are located at the beginning of each microkernel are mixers E0 and E1. Let's take a look inside them and see how they work. As you can see, inside each of the mixers there are 2 rows of 32 double-D triggers, the top one and the bottom one. The top row receives a 32-bit number which was calculated in the previous microkernel. For the mixer E0 it is number A, and for the mixer E1 it is number E. After the number completely enters the mixer, its input mix receives a mixing pulse and the data is mixed in combinational devices that are between the rows of D triggers, and they consist of 2 logical exclusive OR elements. For example, to get the least significant bit of the new number, bits 2, 13 and 22 are mixed, and to get the 5th digit, bits 7, 18 and 37 are mixed. After mixing, the received bits are written to the bottom row of D triggers and begin output from the mixer circuit to the conveyor for further processing. As you could understand, the microkernel is very simple, and the only difficulty in its design is the need for very accurate synchronization during data input and output. Our microcore is small, simple and fast. But we didn't stop on the obvious advantages of the serial architecture. Therefore, after the end of the main core development, we carried out a series of optimizations: conveyor, logic and transistor. All these improvements have given us the smallest equivalent core in the industry. The classical core for a Bitcoin miner consists of 54,558 gates. Our equivalent core contains only 19,664 gates. This is almost 3 times less. It's time to calculate the performance of our architecture. To do this, we wrote a program in Python, which you can now see on your screens. As you can see, all calculations are made for the minimum and maximum operating voltage, namely for 0.45 volts and for 0.7 volts. Let's look at the results of its calculations. The length of the longest chain of logic elements is 24 gates. The worst response time of the chain is 72.72 hundredths of picoseconds. The best response time of the chain is 45.76 hundredths picoseconds. The minimum estimated clock frequency is 13.7 GHz. The maximum estimated clock frequency is 21.95 GHz. The equivalent micronucleus capacity is 19,664 gates. Capacity of the core of the cool conveyor is 2,399,040 gates. The number of equivalent micronuclei on a chip is 76,860 pieces. The number of full conveyors on a chip is 630 pieces. The minimum performance of a single chip is 456 GHz per second. The maximum performance of a single chip is 725 GHz per second. The minimum performance of the miner, which consists of 256 chips, is 116 THz per second. The maximum performance of the same miner is 185 THz per second. The minimum consumption of one chip is 7 watts. The maximum consumption of the one chip is 25 watts. The minimum consumption of the miner is 1,792 watts. The maximum consumption of the miner is 6,448 watts. Now let's enter the data into the mining profitability calculator and see the result. The calculation is performed as of the 14th of March, year 2019. Used calculator miningbitscoinguide.com. We input the performance of our miner, power consumption and the cost of electricity per kilowatt. Click Calculate Profit and get the result. Our miner for each month, without taking into account the recoupment and commission of the pool, is capable of generating a profit of $417.43. Now let's compare the characteristics of our miner with the ones of competitors. Today we have 6 main competitors which manufacture miners based on 7, 10 and 14 nanometer technologies. These companies are Bitmain, Bitfury, Canaan, Silicon, 111 and GMO. Unfortunately, we couldn't find concrete data on miners of the Japanese company 111 since their miner is still under development. Therefore, we will conduct a comparison only with those miners whose technical characteristics are already known to us. I propose to look at the comparative table. As can be seen from the comparative table, the characteristics of miners made on the basis of comparable technical processes and based on a parallel architecture are very close in their basic parameters. The specific productivity of all miners of competitors differs only 2 times, while our miner made on the basis of serial architecture is 3 to 6 times ahead of competitors. Both miners of the Japanese company GMO as well as the miner of Silicon turn out to be unprofitable. However, buying profitable miners from Canaan, Bitmain and Bitfury also doesn't make sense because it will take from 122 to 300 months to pay back them. And only our miner made on the basis of serial architecture looks like a confident leader with a good safety margin. Its total advantage in profitability compared with the miners of competitors is from 14 to 56 times. These data show clearly that new architectural solutions are a competitive advantage in modern conditions. It remains to calculate the net profitability of mining at the Venus miner for the current year, taking into account its payback. 12 months minus 2.9 a month for payback, then multiply it all by $417 and get $3,794. Well, now you know what advantage our miners give in the conditions of modern crypto winter. For anyone who wants to be acquainted with our developments in more detail, on our website the kernel source code is posted in Verilog and the test bench created for it. They can be freely downloaded from direct links and tested in specialized programs. So the first stage of our project, whose task was to develop a promising and superior to all modern allergies chip architecture for Bitcoin miners, was successfully completed. The technical characteristics of our chips exceed the characteristics of competing chips several times. The size of the third-party investments used by the Venus Mine project, which we collected at the pre-sale stage, was $4,800. Now the second phase of the project begins, the creation of a prototype of the fastest miner in the world. The estimated time of its completion is from 8 to 12 months. To finance it, we have launched the second stage of fundraising, pre-ICO. The total amount of tokens offered for sale is equivalent to $200,000. Anyone who is interested in acquiring our miners or making a profitable investment at this stage of raising funds can acquire tokens of our project with a 50% discount. After the completion of the third phase of the project, our tokens will be the only means that will allow you to purchase Venus miners. Therefore, it is most advantageous to purchase them right now, as long as a discount for secondary investment applies to them. Well, in this video we have completely explained the work of our architecture, and now any crypto enthusiast has a new topic for reflection. We hope that you learned something new from the video and learned the essence of our project. We thank you for your attention. This was a Venus Mine project. Venus Mine is the fastest miner in the world.